Congratulations for making it to the last video for this chapter, last lecture video. I know it was a long chapter, but there were lots of little pieces that needed to come together. So in this chapter, we introduced the concept of valence electrons, used those to determine the Lewis dot structure for a molecule. And from that Lewis dot structure, be able to say its Vesper notation and the shape or the molecular geometry of that molecule. And then in the last video, we talked about this concept of polarity or separation of charge in a covalent bond. And in this video, we're going to take that same concept of polarity and differences in electronegativity to say something about the polarity or separation of charge in a covalent molecule. Being able to say if something is polar or not is really important in so many ways. Water's a polar molecule. It can only dissolve polar substances. So polarity plays an important role in lots of different properties of molecules. This little video is just going to talk about how can we determine, based off of the concepts we have talked about so far, how can we determine if a molecule, an overall molecule, is polar? Because you would think, as I remember thinking when I was a intro chem student, that if your molecule has a polar bond in it, if part of the molecule has a polar bond to it, then the overall molecule must be polar. Well, it turns out that is not the case. Presence of a polar bond does not necessarily mean that your molecule is polar. You have to know something about the shape of the molecule as well. What do I mean by that? Let's look at CO2 and H2O. Okay. I have the Lewis dot structures here for each. And for both, I have shown the polarity or the difference in electronegativity with these arrows, with these dipoles, kind of like what we talked about in the last video. Those dipoles point from the atom that is least electronegative to the most electronegative atom. So in carbon dioxide, I have one dipole going from carbon to one oxygen, a second dipole going from that same carbon to a different oxygen. In water, I also have two dipoles, both of which are pointing toward the oxygen. So both of these molecules have polar bonds. But what do you notice looking at the polarity, looking at the dipoles or the arrows between carbon dioxide and water? What do you notice that's different? For the carbon dioxide molecule, those arrows are pointing in opposite directions in the same way. It's kind of like doing 2 steps forward and 2 steps back. You don't really go anywhere. So the polarity of those two bonds is the same due to its geometry. Thereby, the overall molecule is nonpolar because these two dipoles cancel each other out. So the overall molecule is nonpolar. Let's look at water. Here's the two dipoles. Looking at those arrows, and maybe even these pictures down here is maybe shows it a little better. Do those two arrows cancel each other out? And the answer is no. They don't cancel each other out because of the lone pairs of electrons here. This water is not a linear shape, it's more of a bent shape. So there's more electron density by the oxygen than by the hydrogens. So therefore, because of those lone pairs of electrons, this overall molecule, water, is polar. That means that there is a permanent separation of charge, permanent separation of electron density in that molecule. And you may say, okay, that's all well and great, Mrs. LaPola, but so we can't use the presence of a polar bond to determine if a molecule is polar. What's a quick and dirty way to figure out from a Lewis dot structure if a molecule is polar or not? So I have summarized a rule here by the blue star that will work for all molecules that we will talk about in this class. If you go on to Chem 1, I can think of a few exceptions to this, but we will not talk about them. The rule is the quick rule of thumb when determining if a molecule is polar or not. And you will have to do this not only for your exam, but for your Lewis dot structure lab. For molecules in this class, if the VSEPR notation is AX2, AX3, AX4, and X is the same atom, then the molecule overall is nonpolar. Otherwise, in all other instances, so if X is a different atom, or if you have lone pairs of electrons on your central atom, the molecule will be polar. So I highly recommend when doing the Lewis dot structure lab and when taking the Unit 3 exam that you have this slide or at least this rule of thumb available to help you determine if an overall molecule is polar or not. So here are 3 structures that we've talked about previously with regards to the Lewis dot structure and their molecular geometry. We can now go back and look at them and see if any of these molecules are polar or not, using the rule that was in the previous slide. So for CFCl3, I do have an AX4 notation, VSEPR notation, but is X the same atom? X is not the same atom. I have 3 chlorines and 1 fluorine. X is not the same atom. So there's actually going to be a slightly more electron density by the fluorine because it's more electronegative than the chlorine. So since X is not the same atom in this molecule, CFCl3 is a polar molecule. BH3, AX3 notation, X is all the same atom. So this molecule would be nonpolar. Last but not least, SeO2, AX2E. Oh, I've got lone pairs of electrons on the central atom. That presence changes not only the geometry of the molecule, but according to the rule from the previous slide, also makes this molecule automatically polar. Okay? So you should feel comfortable being able to, after this chapter, you should feel comfortable being able to do the Lewis dot structure for a molecule. Give me the VSEPR notation, the geometry, and then say something about the overall polarity of the molecule using the rule from the previous slide.